Hello everyone, and welcome back to my channel. In today's video, we are going to learn how to calculate for some very important parameters for our RF vacuum tube oscillator. You can use a similar calculation for the parameters of your HF VTTCs or your vacuum tube induction heaters, or even you can calculate for some low-frequency vacuum tube Tesla coils which will operate at around a few hundred kilohertz. So now let's start from the very beginning. This is the circuit of this RF oscillator, but with a different kind of feedback. I simply use this schematic for the calculation because it will be easier to understand. And this is a Hartree oscillator, which you can see in many typical HF VTTCs. They will just have another output matching coil here, which is used to match the plasma's impedance to the resonant impedance of this tank circuit. And to achieve high efficiency and high power, we need to operate the vacuum tube under Class C mode. Here you can see some anode current waveforms, and the conducting angle is less than 90 degrees, which means the tube is under Class C operation. And to achieve high power in a very short conducting angle, we need a rather higher anode current, which means our grid of the tube will be driven to the positive region. It will have a positive voltage against the ground among some of its operating cycles. So that means our grid current will be larger than in Class A or Class B operation. To understand these three waveforms, we need to first understand what is the grid current. The grid current can only exist when the grid is more positive than the ground, and the cathode together with the grid actually forms a vacuum tube diode. So the current can flow in this direction, right? And that will induce the grid current. But we know that the total amount of current from the cathode is a certain value. So if the grid is more positive than the anode, which I mean is that in a post mode, because during the calculation sometimes you will find that the anode current actually is larger than the peak current the cathode can supply, or in the situation that the grid potential is much higher than the anode potential, then the anode will just be blocked, right? So all the electrons from the cathode will move to the grid to form the grid current. That is what you will see in these two waveforms. Why the anode current has a small part missing. This is not a small part, a very large part. That means anode voltage actually touches zero, nearly zero, which we will see in the calculations soon. And in that way, we can get a very high efficiency of the tube. But that means we need to have the grid be driven at a much higher voltage or potential than the anode. So let's start our calculation. First, you need to, actually I have calculated for several tubes, and I just pick out two calculations which I wrote very clearly. This one is for the TB3-750, and this is for the 7T85RB, which is made by Toshiba or Canon, an inductively a triode which is used for industrial heating, RF heating. And first you decide your anode voltage, which will be limited by your anode supply in most situations, like this one here. And also you will need to design your output power, your needed RF power. And to get a very high efficiency, you will use a conducting angle. I recommend 70 degrees. The first reason is that by using 60 to 80 degrees, you will get high efficiency, and usually your maximum anode current will not go beyond your tube's maximum cathode emission capability. If you just use some very normal power range, do not exceed too much over the PDF documentary. So the first thing we need to do, also here, the transconductance, you need to get that either from the PDF documentary, or you can simply calculate it by yourself. And the amplification factor and this D constant, actually the amplification factor times the D factor will equal to 1. I mean, you know what I am going to say, but I can't express myself in English well, sorry. And the internal resistance is just here. We don't need to use this one, but among vacuum tubes, a very famous equation says that the transconductance times the internal resistance actually equals the amplification factor. So if you know 2 of the 3 numbers, you can calculate the last one. And this is not the transconductance. It is a very strange constant, not a constant, a coefficient we need to use. You can calculate it in this way. Like this is the characteristic curves for this tube, and in that curve, among the curves, you can see that here is a line which changes rapidly, and the K of this line equals to this coefficient. Okay, the K of this line equals to this coefficient. And here, oh, the focus is bad. We need to calculate this one by using this formula. You see the designed power, and this constant we just calculated here, your anode voltage, and this constant, which will be 0.436 under the condition of this just 70 degrees conducting angle. So you can get this one, and you need to get this coefficient, which is around 1 to 1.02 times this constant. Here I simply use this one. This means that the anode voltage actually will not touch the ground. It will be higher than the ground, but it will much lower than this one. It will look like this, just slightly higher than this one. And if you use 1 in this equation, the anode voltage will just swing to ground, which I have wrote here. And you will get this coefficient. And this is just for some test I did. You can just eliminate this line. And the maximum voltage appeared on the anode will be this. You can calculate it by using this and the anode voltage, and the maximum anode current is this, the peak current. You need to make sure that this current is less than what your tube is capable of. Your cathode emission need to be larger than this number. And this, I do not know how to say it in English, sorry, but you can simply see that we can get this number from this one, and a ratio between these two values, right? Get this one. Oh, sorry, that is not the maximum current. The maximum anode current is here. You can see I just checked it because it's under the capability of my tube. This is just a harmonic current of the anode waveform, and this will be the maximum current, and this will be your anode input power. You can calculate it, and you can calculate the anode dissipation by just do a minus between this one and your rated power. So also this is a safe value for my tube, and you can calculate the efficiency if you want to. And this is the load resistance when your anode is in resonance, and this you can calculate it. This is a rather important value because this will determine how well your load is matched to your oscillator. In this tube it is 4.4 kilo ohms, and you can see in this larger tube the resonant anode impedance is just around half of that value, and the larger your tube is, I mean the higher the power is, and usually this value will be less, but it will usually lie around 1 to several kilo ohms. Keep that in mind because you can use that to check your calculation. And this is the maximum gate voltage. You can see here we just utilize the maximum anode current, the transconductance, and this value, which you can calculate from here, right? So we get, oh no, not that one, this one. So we get it, and the D, do you still remember what is that? It is here. And the maximum anode voltage, so we get the maximum gate voltage, and this is another coefficient we need to use in this equation, but we need to get it first. I still need to tell you how to calculate for it. If you check your PDF documentary of a vacuum tube, you can also see this kind of a graph, the anode current against the gate voltage. So you choose a line which represents the working condition of your input voltage, and this line will have a cross with this XL at this value. This is usually a negative value, which you can put in here, and you need to draw a line at this certain point, which means that the point has the maximum anode current value in your calculation. Also, it is on this line, so the voltage is your rated voltage. And you need to draw a line which has the same K factor at this point and make a joint to the x-axis, and you will get the second value we needed in this equation. Normally, these two values are all negative. Remember that. So we will get a negative value here, which you can see for this tube it is minus 120 volts, and this voltage will need to be plus with the D factor times the anode voltage, which is here. Luckily, it's just 0. But in another situation, it is 40 volts. Usually, the voltage at the grid, the starting point of the grid, is a positive one. But if you get a 0 voltage or a slightly minus voltage, it may also be reasonable. And the next step is to calculate this one, the static situation for the grid. We use the value we just got and do the calculation here. This one we know, this you're designed. This one we just calculated. This we know, this also known, this also known, so it's not hard to get this number. And the maximum gate voltage, I guess you already know how to do that. Just this statistic situation plus the maximum voltage, then you will get the maximum gate voltage. The minimum voltage you can just do sorry, that is not the gate, the anode. So to get that, you can simply, by using this equation, the anode input voltage times 1 minus the factor you just calculated, right? So this voltage is actually means how high this point will be above the ground. So as we can see, if this value equals to 1, this equation equals to 0. And if this value is less than 1, we can see that it actually goes up, right? You can see that is the value. And by utilizing these two numbers we just got, we need to refer to the graph, and we will get your maximum gate current. To know how to do that, let me find a graph if I have that graph. Oh, great. Anode voltage and great voltage. Oh, here I just have a graph plotted by hand, and remember that we get the maximum gate voltage and the minimum gate anode voltage. We can see that here find our gate voltage, here find our anode voltage, and sorry, because this is for another tube, the values will not match. And for example, if the anode voltage is 1 kilovolt and the cathode voltage, the grid voltage is 300 volt, we can see is here. So we can just read out what our anode current and grid current will be. Here is the region for looking for the grid current, and this is looking for the anode current. So just by doing that, we can get your grid maximum current So we need to do another analysis here to use this value. The grid voltage minus grid voltage you see here. Because this is a -1, so we want to get a positive value. To use this one divided by the voltage swing, half of the voltage swing of the grid, you can get a cosine value. And refer to a table, we can get that these two constants, which is actually the same meaning of these values, but it is for analyzing the grid waveform, and we can simply get our gate current, grid current, and grid maximum current, and the power we need to get to drive the grid. And this is the power loss in your tube's grid, which will minus the power loss on your grid resistor. Remember, this is a negative value, so the plus actually means to minus out the loss in your grid resistor. You can see here is just a DC power, so the total power minus this will be the power in your tube's grid, which you need to check if it is smaller than your tube's tolerance, and you can finally get your grid resistor's value. Use the positive value, so you will add a minus here, right? And this is actually the feedback ratio, the minimum feedback ratio you need to get. Simply the maximum grid voltage divided by the maximum anode voltage. In this situation, it's 0.1, and I suggest you to calculate this. The anode DC current divided by the grid DC current. By calculating this value, it will be easier for you to tune your oscillator. We just go over all of the calculations we need, and now let us talk about how to tune the oscillator. In this situation, it's a Colpitts oscillator. You can see this capacitor together with this one actually forms a voltage divider for driving the grid. And you can see 240 picofarad, and this one is 68 picofarad. So the feedback ratio is actually larger than 10%. I recommend using 2 to 2.5 times this value. That will means 20 to 25% feedback ratio to get a rather stable oscillation. First, you power it up, but at a lower anode voltage than you designed, and to use some neon discharge lamps or some ampouled gas, which can be put close to the anode or the resonant coil to see if the oscillation has started. And if the oscillation is not started, you can just move away the grid leakage capacitor, which is here, and that will give your tube a lower grid negative bias to just for better start of the oscillation. And if you did that and it still does not oscillate, you need to check your feedback ratio. Normally you need to increase this value, but please do not increase it to too much. You will risk your grid. In Hartree oscillator, which means a transformer feedback oscillator, the oscillation will start more easier. So that's all about how to get the start of the oscillation, and then how to tune your oscillator. You need to have some load inside this coil to get the working condition to your calculated values. You need to get a load for it. So you can just simply use some iron, which can be inserted into the resonant coil. Here, use some iron in it. What I use, you will see very quickly. And when you slightly insert the iron into your coil, the first thing you need to check is your cathode current. You will see the cathode current normally goes up, but in some situations the current will go up, and then suddenly goes down. That means the feedback is not enough and the oscillation actually stops, or it just stays on some parasitic oscillation frequency. And in that situation, you need to increase the feedback. But if you are doing that at a fairly low voltage than designed, then the cause might be it is same reason, not enough feedback, but the reason might be just the voltage across the tank is not enough for sustain the oscillation. So in that situation, you can also try to increase the voltage to see if that situation happen again. Or if you see the stop of the oscillation starts at a higher voltage, if you at a higher load, at the higher load, if you have increased the anode voltage, that means that your feedback ratio might be reasonable, and you can increase the voltage to the anode while gradually tuning it. And another thing you need to look at is your grid current. Normally when you insert your load, the grid current will go down. That is because the feedback will not be that strong than before you insert your load. So the grid will be driven to a less positive potential than before, and you will get a less grid current while getting a larger anode current. And you can do this tuning gradually, while gradually increase the anode voltage until you got what your design anode voltage is. And at that time, you need to check your anode current, which you can also see it as a cathode current. And you need to also check your grid DC voltage, which is this one. And you can actually check the ratio between these two values when you have just finished your calculation. Normally for a serrated tungsten filament vacuum tube, this value should be around 10% to 25%. Remember that, 10 to 25%. And that's just for that. And the next thing I will tell you is how to kill the parasitic oscillation. Sometimes in a vacuum tube linear amplifier, I mean for HF band, they simply add a choke which is mounted onto a low resistance resistor and connect it between the anode and the output pi network. That can kill the parasitic oscillation. And here I simply use the same method, but connect it in the grid loop. Also, do not use some doped blue small capacitors, which you can easily see in some switch mode power supplies in such a high power RF generator, because the grid feedback capacitor also need to withstand high reactive power. Once I try to parallel to that kind of blue small capacitors, which has around 1 centimeter in diameter, not a very small one, and they got burned in a few seconds. So I simply use a 12 kilovolt 510 picofarad ceramic capacitor in series with a grid feedback loop. And the importance of the capacitors in the resonant tank, I think I do not need to talk about that. You all know that. And also the DC blocking capacitor here, from the anode to the resonant tank, it also needs to withstand a high reactive power. And I recommend some ceramic silver plated capacitors as well. That might be all about today's video, and I feel that I just talk about these things in a mess, and I hope you can understand what I am going to say, and just watch my experiment from now to the end. Okay, and now let's do the experiment. First, please let me to make a brief introduction of the whole setup. The RF generator, a plate of water which is my dummy load. As you can see, the induction coil is magnetically coupled with the plate of water. The cooling fan is in operation. This is my grid current meter. The original meter I used yesterday was burned due to the RF, and this time I just tore this meter down from another device I made, and the fourth scale means 1.6 amps. So each of the small scales means around 66 milliamps. 4.5 kilo ohms of grid resistor, and the grid leak filtering capacitor, grid choke. Here, as you can see, is my HV power supply, and unfortunately the high voltage meter, which was originally a 50 microamp meter, was burnt due to the RF signal yesterday. So simply I'm using this multimeter, 50 microamps, this one, as you can see. So each scale means 1 kilovolt. So 1, 2, 3, 4, and 5 kilovolts. And this is a cathode current meter. Each one means the fourth scale means 2 amps. So 200, 300, and 400 milliamps. And as you might remember here, our design power output is 900 watts, and the design voltage is 3 kilovolts, while this power will be achieved at around 0.37 amps. And the grid current, as we just talked about, is around 37 milliamps. So let's do the test now. Firstly, I will increase the high tension to around 3 kilovolts, and we will first look at the cathode current, and then we will look at the grid current here. At last, we will see how this circuit performs. So let's just begin. Maybe you can hear the humming noise now. Now it's 3 kilovolts. The cathode current is actually 400 milliamps. Oh, I turned the flash lamp off. Just 400 milliamps. and the grade current around 60, actually a bit less than 66 milliamps, and the room temperature water is actually going to boil now. The grade is just a little bit cherry red because the plate dissipation we calculated here just over 200 watts, and this tube is capable of handling 350 watt plate dissipation. Okay, now the water is boiling now, and we see that the grid current is a bit less than just now. Also, the cathode current is a bit less than 400 milliamps. Okay, now let's stop the test, and the water is still quite hot. We can touch this feedback capacitor, which is a bit hot. The resonant coil, I guess it's around 70 to 80 degrees, and the resonant capacitor in the voltage divider setup a bit warm, and this very large capacitor also around 40 degrees now. The tube space is just slightly warm, which will be good because the pane, actually at the joint of the pane and the glass, the temperature cannot be exceed than 220 degrees. So what we just see is that the system was drawing around 400 milliamps of current at 3 kilovolts, and the grid current is around 60 milliamps, which are a bit larger than we calculated here, right? Also, the cathode current is a bit larger. That is because we do not taking the loss of the tank, and also the load here. If you can see that I'm just using some a rubber, a cup, and some cards to sustain this one, and the distance between the coil and the plate is not very suitable to get the load impedance to this one, 4.44 kilo ohms. The load is actually less than that, so the power needed is actually a bit larger than 900 watts. So the cathode current will be higher than we designed. But why is the grid current higher than 37 milliamps? That is because of our feedback ratio. Here I'm using around, let me see, around 20% feedback ratio. But as we can see here, our calculated feedback ratio just around 10%. So to sustain a stable oscillation, you need a feedback ratio a bit larger, usually 2 to 2.5 times the designed feedback ratio. So I just simply use 2 times the designed feedback ratio, but that will lead to a larger grid feedback current, and that also means that the oscillator is dangerous to operate at under no load condition at full power, because you will risk your grade, right? The grade dissipation will be higher than your design, many times higher, around 4 times higher in this situation. But since our grid dissipation is around 4 watts, if you just operate this thing under no load condition, the grid dissipation will simply go around to 16 watts. So still within the limit of this tube, but you will get a very large reactive power oscillating in your tank circuit, so your coil and your capacitors will be risked. Also your bolts here, and if you also use a bolt to connect at that joint. So this is all about today's video, and I hope you can learn something from it. And if you have any questions, you can just simply leave your comment under this video or email me.